Okay, we're back. Here's an example of a shielded metal, submerged arc weld filler metal example, right? Flux composition, electrode, medium, 12K. All right, so each one of those breaks up just like we did. I'm not going to go too much more in depth with that. Here's the equipment. Naturally, you can see there's a wire feed coming through here, being fed into this. It's usually a very large size material as well, a large size wire. Here's your hopper. It's usually got a flex tubing. As you can imagine, it's got a sand or a granular flux, just like cat litter or sand. Typically, it can hang up, can be a little bit quirky as far as clumping together. It's particularly also with moisture, right? So you want to, this usually needs to be, can be done outside. Usually has to be in some sort of an contained atmosphere, to where it wouldn't get rain on or so forth, things like that. All right. So high deposition rate, deep penetration, it can be mechanized, a handheld process. You don't see very many handheld processes, I can tell you that right now. Good for overlay large areas, high operator appeal. I don't know about that. Anybody that I've ever talked to that's welded this thing has just been bored to death after a little bit of running it. So first day or two seems really cool, and then after that I think you're pretty much done. Okay? Flat or horizontal fillets only. Basically you're going to do a lot of weld buildup on this. Usually you're not going to see, and that's not entirely true either, because I've seen submerged arc welds on groove welds and butt welds all the time. Particularly Caterpillar, say they're doing large castings and framings together, you'll see submerged arc done on them. Okay? So, get rid of that one by far. It does need positioning. It does have an extensive amount of setup time, so forth. Discontinuities, groove alignment, see, totally contradicts itself. Flat or horizontal fillets, and then groove alignment alone. So, we've done this with pipe. Usually what you're going to see this for more than anything is like building something heavy up, okay? Or joining large pieces of casting together, so forth, all right? Slag inclusions can also be not just slag, but can also be sand or grain or flux, because they haven't turned into slag at that point. Incomplete fusion and cracking width to depth ratio. So here's what we're going to talk about. The one thing is you can join, so you can go down 2 inches thick, but the benefit of this is the groove only has to be maybe 3/4 of an inch wide, right? If we were to do a 2-inch thick piece of steel by hand in order to get an electrode down in there, we would need to be close to 2 inches thick wide as well, right? Or do a double V groove, top and bottom both, in order to maintain that. In this situation, you could just have a V groove like here on the right, do 2-inch thick but only 3/4 inch wide material. However, since the weld pool solidifies from the outside of the edge in, and then it solidifies, and then all residual stress can crack and pop here in the center, is exactly why submerged arc welding is acceptable to centerline cracking. Okay? In this case, you need to slow down your heat, take your heat down a little bit, maybe slow down your wire, slow down your rotation, your movement, your speed, travel speed, things like that. Start looking at it. Compatibility of materials, and also you might need to increase your heat input at this point, or amperage as well. Excuse me. Plasma arc welding shows a good picture there basically of the arc. The difference here between TIG welding and this one is, number one, you have a chamber basically to help punch the hole through, right? So every one of these, this isn't going to be something to just fuse on or lay in here. This is what we refer to as keyhole welding. Basically the big difference is plasma arc welding does exactly what it does in plasma. It punches a hole through it, and then it comes back in and you add filler metal to it, or if you're doing it autogenously, to where it fills in behind you. A good comparison to this would be if you're trying to weld thin material or cut with an oxy-fuel cutting to thin material steel. You know, a lot of times it kind of filled in behind you as you're coming along, like you watched a keyhole, but then it all of a sudden filled back up on you as it was going through there. Okay? So you got 2 different nozzles, 2 different chambers. One's to punch a hole through, the other one is for gas or shield. All right? Transferred, this is non-transferred arc. Number one, as you can see, the work is in the base piece. The electricity, you can have it in the work piece or the ground. and then only a positive supply here, very similar to TIG. This is the opposite one. There's no ground whatsoever here, so it's just coming in, basically laying on top of it as well. So I've never seen it. Here's two examples. Here's what you talk about. If you see something referenced keyhole welding technique, it's usually the plasma arc situation at this point. Okay. Tints arc, deep penetration, clean process, shielding gas only, low tolerance for contamination, complex equipment setup. Naturally, you could tell just a little bit of misalignment would be a bit of an issue, right? And, you know, the equipment itself takes a little bit of a while, making sure everything's at the right spot, especially if you don't do it very often. Discontinuities, naturally tunneling. Anytime your penetration through there, you can get some wormhole, keyhole stuff. Tunneling is exactly what I would talk about earlier with, you know, kind of the sucker hole inside of the GTAW root, okay, leading all the way through. Copper inclusions, naturally, because it's, you're running through with plasma, so you're taking a chance of getting some off your first chamber here. Knocking some of these pieces off right here and getting it all over the place and some copper from it, okay? All right, electroslag welding. It's a pretty cool setup. For the longest time, it wasn't used on bridges here in the U.S. It used to be for bridges all over in the U.S. And then they started to realize that there were some fusion problems with the processes and the way they were doing them. So they banned them from the U.S. for a while. And now with, of course, in the last 20 years, the technologies that's come back pretty full force, you can actually weld even up to like a 45-degree angle. Okay, so this is the conventional way. See if I'm missing something. I do want to go back real quick before we get into that. Plasma arc welding. I want to talk real quick, once you look at page 323, and it says the plasma arc welding, the next process to be discussed is plasma arc welding. Plasma is defined as an ionized gas. Any process using an arc, plasma is created. However, plasma arc welding is so named because of the intensity of this plasma region. At first glance, PAW could be easily mistaken for GTAW because the equipment required is quite similar. Okay? You see also talked about as ionized gas as well, and particulates. You might see that in a plasma arc welding setup. Or question, I mean. Okay. Electroslag welding, back to this one. We're on page 3-26, right-hand column, top side. I'm going to read from the book for a second. Second sentence down starts out right-hand side. Even though the welding progresses vertically up the joint, the position of welding is considered flat due to the location of the electrode with respect to the puddle. Okay, so this is no different than a groove weld, right? All of us in the groove weld know that even though the weld comes up vertically, the material fills up vertically. Remember I told you it's off of the electrode. So the electrode at this point, you're welding it flat versus welding it horizontal, vertical, or overhead. It's not the position of the weld, but the way that the electrode is. So even though this weld fills up vertically, which you may see a question that says, what type of welding would have a vertical progression of weld, but done in a flat position? Something similar to that. And in that case, you know the weld comes up vertical, however, it's considered to be flat because gravity is keeping it all down at the same time. Okay? So here's a good example, and I'm going to show you, I'm going to talk a little bit about railroad tracks and how they used to join those together. And this one shows water in and water out. So this is very similar. So looking at these two pieces, I want you to think of joining two railroad tracks, okay? Heavy, thick iron. You can take these two pieces, railroad tracks, stack them up, put them next to each other with a small gap between them, okay? You have these two copper shoes that come in there, form-fitted. They've been machined to fit exactly around this railroad track, right? Railroad track is perlite. It's at 0.08% carbon. It's a very crucial stage right there on the iron-carbon transfer. It's important. It's a very, it's amazing steel, okay? Let's look at that. Moving on. Basically, in order to do that railroad track, you'd have to cut it down the center, you'd have a lot of distortion, a very brittle weld at that point when the train's coming across it, and it could crack and do a lot of stuff by the time you welded it up. It can still be done manually, but some care needs to be taken to get there. However, it would take forever to weld that up in a situation like that, and if you had miles of track to do, it could be an issue. So what they've done is they've sped this up, right? So they bring it in there, they put these shoes in there, they bring a power source out, and so basically there's a little hole in the top of this, which in this case is the consumable guide or electrode, and you can start this process and you can start welding it, okay? And you fill it up from the bottom up, and it falls to very much like a casting. Just fills up liquid, comes out the top, and you're done, okay? However, it's not a casting, because then we wouldn't have as great a fusion into those pieces. In that case, you'd end up with cold shuts and lack of fusion if you were to just pour liquid metal in there. You need and require the heat and the friction to be accepted between both work pieces and get that great bond in between the two. And it does have a slag that fills up all the way up on top of it as well, okay? Comes out the top. So an interesting, page 3-26, reading from that right-hand column, second paragraph, an interesting feature of electroslag welding is it's not considered to be an arc welding process. So here, the arc is used to initiate it, right? To initiate the beginning stages of it, but then let's read the rest of it. It relies on heating from the electrical resistance of the molten flux to melt the base and filler metals. So it's somewhat of a chemical reaction at this point. Now this is not to be confused with thermite welding. Thermite welding, you might see an electrician. A lot of times you build a jig for something to go on the side of a building, so you can get a ground clamp to it, right? You got this little fixture with a threaded piece into it. And instead of welding each piece, you know, the electrician doesn't need to carry a welder around with them all the time. They just carry this little jig, and they'll set this pot of, they put the jig in there, clean this spot of the material, set this up against it. They put a charge of magnesium liquid on top of this little thin disc, okay? And what they do is they ignite it with the striker, burns super hot and bright, and as soon as it hits the right temperature, it melts through that disc, comes right in, and it bonds and fuses itself and welds right to the side of that building, okay? And at that point, now the electricians have a grounding clamp that they can make sure that their circuits, their panels, and everything else is physically grounded to the earth at that point. Really important. But again, it's not holding a stress situation, it's holding a ground piece. And even that, you have to have a thud test and make sure that everything's in the right position and so forth. But that way they're not running around with an arc welding process and a whole other set of gear at that time. Okay, that would be considered thermite welding, totally different situation. Some advantages of this, we can read through these, okay, limitations. Naturally, it is somewhat of a casting process, so there's always a chance of lack of fusion, so forth. A little bit of prep is important. Make sure you don't have a lot of contamination in there. An extensive setup time as well, right? ESW discontinuities, porosity, slag inclusions, large grain, shrinkage, cracks, all stuff that you can have in casting. All right, moving on. Oxyacetylene welding. We're on page 327. Most of us know this, or we're familiar with it. Not to be confused with cutting, different process. Same fuels, different process, right? So in this case, quite literally, we have a oxyacetylene setup. Now, this is not to be confused with oxy-fuel welding. In this case, it specifies acetylene is the type of fuel gas that we're using. Oxy-fuel welding would be very broad. You can use any fuel gas, MAP, propane, butane, acetylene, so forth. This one is exactly OAW, okay, and that's how it's listed. So here we have the oxygen, the acetylene, they mix inside the tip. The torch tip here is much different than a cutting tip. A cutting tip, the two gases stay separate up until the point to where they leave the tip, and at that point they're ignited. And even then, they're separate because the outside are acetylene, the internal one, the center hole is oxygen, right? For welding, they're both mixed. As soon as they come out of the torch body, they're mixed in the same nozzle at the very beginning, okay? And your rosebud here is the exact same way. Here's the problem with the rosebud is people have a tendency to get so hot, this end is brazed on, silver brazed on. I've seen that end come completely off because people sat there way too long and let that piece get way too hot. and create an issue. You can get some back pressure in there and start a fire in the chamber as well. Okay? But basically it is what it says. The oxygen acetylene mix, naturally this is running a neutral flame. You got your acetylene feather, your cone, direction of travel. You can do you know, in this case a lot of times you want to be dipping as you're going, kind of a push pattern. You can do it as a drag pattern as well. Okay? However, you're using a filler rod, again ER70S-6 or 2, preferably. Very simple setup, very simple equipment. Can be used on aluminum. You can braze aluminum, you can weld aluminum, brass, bronze, stainless steel, and that's brazing. We'll talk about that here in a few. But this equipment can be used for a lot of things, including the cutting process, right? Filler metals are basically RG45 or RG60, okay? 60 is also very similar to 70S-6, okay? Again, that is the tensile. Suitable for thin materials, very portable, no electricity required. However, it's a very slow process, and depending on where you're at, it's a lot of concentrated heat, and there can be a fire hazard as well. Flame adjustments, and it's a slow process. But out in the middle of nowhere, sometimes it's the only option you have. Severe oxidization, you can get a lot of carbon in there, especially a lot of black soot can be in there. You got to keep it clean, make it brittle, so forth. We'll talk about cutting here in a few. Let's move to stud welding. All right. Look at this stud he's welding. Yeah. All right. So stud welding is actually the fixture in which we are welding. Okay. So this one shows it a little bit better. And a stud gun is actually just what it says. It's a gun that holds this piece. Okay. So the picture's showing you. Let me give you a better example of this. But just to make sure we're on the same page, okay? So as we're coming along here, the stud gun's holding this piece, and this is a threaded bolt, say a 1/2-inch bolt to be able to bolt down a catwalk on, okay? So what happens is we come down, we touch, and when we touch, it makes initial contact and starts the electricity, the ground to the base workpiece, okay? And as we pull away, all of a sudden, at this point, all of, showing you up here, the electricity is going between the two. It's heating up and melting this, and it's heating up and melting this base piece, so creating a liquid puddle on the bottom, as well as, like my 60-10 or 70-18 electrode, this is actually working as my electrode, okay? And then all of a sudden everything's hot and molten, liquid, and it pushes in, and then at that point it shuts off as soon as that makes contact, okay? And it just stops, and then everything solidifies around it. And typically what you would see here is you'd want to see, make sure you have a good weld, almost like a fillet weld, all the way around this thing, okay? And one way that we can do this is we give it a tap test or a hammer test. So we whack it, and we either listen for the thud or the ring. It tells us if they're good or bad, okay? Here, multiple, now that you see some of these different studs and fasteners, you're just like, oh, okay, perfect, yeah. I mean, bolt patterns, stuff like that you don't always want to sit there and just weld on. You can use if you're doing 1,000 of these things for a catwalk, the stud gun is the way to go by far. Okay? Flux on the tip cleans the weld area. Standoff tips are also used. So here's some advantages. Some of the limitations, sometimes the equipment does have malfunctions and you have to work with it and so forth. Also, my experience with this stuff has usually been, it's always bid for the lowest bidder as far as materials or the parts. So sometimes, like I've seen the bolt head, you have to come back in and re-grind it, and it's just a pain in the butt, or it's not smooth or not flat. The manufacturers did a poor job because they were half the cost, and so forth, okay? You'll hear things called lack of flash or an incomplete fusion on their discontinuities. All right, laser beam. This is Austin Power's most famous welding process right here. Okay, he's got sharks and laser beams for welders. Some of you probably don't even know what that is at this point. Anyway, light amplification by basically you're going to take a laser, you're going to melt those two pieces down with the laser and bond them together. However, As what we can tell is lasers can be focused or they can be broad. In order for them to create a large amount of heat, they usually have to be a focused light beam, okay? One of the benefits is you could send this thing around a couple different manipulations of a setup with light bouncing off the mirrors to be able to get this fusion, or this penetration, this welding process done. But it's usually a narrow window, okay? Laser beam welding is a fusion joining process that produces coalescence of materials with the heat obtained from a concentrated beam of coherent, monochromatic light impinging on the joint to be welded. Usually if you see some words like that, is exactly what you're going to have to understand is the difference between the two and your other ones. Is a light source, okay? The laser beam has a very small cross section, does not diverge or broaden very often. I'm going to scoot down page 331, left-hand column, third paragraph down. It says the lasers predominantly used for welding are either solid state or gas lasers. In the solid state laser, a neodymium doped yttrium aluminum garnet crystal rods are utilized to produce a continuous monochromatic laser beam output in the 1 kilowatts to 10 kilowatt power range. In gas lasers for welding, the typical type is the carbon dioxide laser, which when we get into, we've got a laser over here. Laser beams can be very focused. They cannot be, some of them are using CO2, some of them normal compressed, clean air now. Lasers have come a long ways in the last 20 years, for sure. But basically, think about our laser. We use it to etch and cut through and weld things. It's the same thing. We can slow it down, change it a little bit, not necessarily to cut, but to weld if we need to also, okay, by putting some pressure amongst the two pieces. So, non-contact process. Okay, here's a good cross section of it, right? So there's the weld just coming down here, welding these two pieces together, very small piece. That'd be pretty hard to get in there. So some types of gearing situations and stuff like that to where it can be mechanized and set up and routinely done works out well for this type of welding process. Advantages, high depth width ratios, right? You can do a pretty thick single pass, you can go up to 1.25 inches, it says. I bet more than that at this point in time. Welds thin metals or small diameter wires as well. So again, if you're going to be using something to set up for a lot of things, small pieces that most people would not be able to weld, or you're finding a skill set, or say even distortion, then this might be the process that you want to start looking at doing. Closely spaced components, so forth. You don't need a vacuum or an X-ray shielding is required. Beams transmitted to many workstations that can be bounced off to different locations, okay? Never seen one. Only ever read about these, okay? Hopefully someday I will be able to see one. I'm sure that NASA and some other folks are using things like this. All right, electron beam welding. Originally required a high vacuum. It can now operate in low or even a no vacuum situation. Fusion joining process. So basically you're taking, this is even better, right?